So let's first briefly go over last lecture's material. We discussed Markov decision processes. So I updated the slides after the lecture. So MDP has a set of states, actions, start state, and transitions. So the policy can be deterministic, which maps a state into action, or stochastic, which maps a state into a probability distribution over actions, over possible actions. So a Markov means that the next state only depends on current state. So the current state captures all the past information. There's no need for looking further back into the past. So for example, for driving task, current vehicle position X does not satisfy the Markov property, since the next state depends on not only X, but also velocity, acceleration, possibly more terms. But if we redefine the state as a vector of position, velocity, and acceleration, then it satisfies the Markov property. So it all depends on how you define your state. So or if your sensor is the camera, if the current snapshot of front camera view can be used as a state. Many people use that. For example, in NVIDIA's end-to-end driving imitation learning work, they used a single snapshot of the front camera view and map it into a steering angle. But many people use the past AM video frames, typically 4 or 6, as a state to capture more dynamics. So here's an example MDP with a single state and two possible actions, left and right. So one valid policy is the uniform random policy. It goes left or right with equal probability. So that's the uniform random. Another policy is always to go left, never goes right. So the third one is alternating left and right. So if the previous action is left, then current action must be right, the next action must be left, and so on. But it's not a valid policy, since it depends on the history of actions. So to be a valid policy, the action must depend on the current state only, based on the Markov property. But we can redefine the MDP's extended state to include the last action as part of it. So a state is S comma last action. Then the policy is a valid policy for the new MDP. Well, in general, in the extreme, you can redefine the MDP's state as the entire history of the MDP. Then it's always a valid MDP. So, but that may be cumbersome. You may have a huge set of states to keep track of. So here's an example MDP. You have 3 states. The green nodes and red nodes are denote two possible actions from each state. So you can mark the states as A or as comma A. So agent taking an action A in state S may get different reward R and next state S prime, denoted as the state transition SAR S prime. So due to environment uncertainty, the same action may lead to different states. For example, if you're playing chess or Go, your opponent's action is the part of the environment. You cannot control it. You cannot predict it. Or if you are driving a car, the wind direction, the road slope, and the surrounding vehicles, they're all outside of the control of the agent. So it's uncertain. So in this picture, all the rewards are 0 except those marked with -1 or +5. So state transition is atomic. So we draw here separate nodes, a state node and action node. But the action node is just for visualization. But you can remove other action nodes and draw a single transition between green nodes. That wouldn't make any difference. So you cannot stop and stay at the right action nodes. It's just a transient node that you must pass through immediately in the atomic step and go from state to state. So MDP search tree, it's like a two-player game. And the actor plays an action based on policy, and environment plays a response. So to return a reward and the next state. So for parts, for the most of the parts, I'll skip because I discussed them last time. I'll just highlight some parts that I changed. So Bellman equations. So there are one is about Bellman expectation equation. One set is the Bellman optimality equation. The difference is taking expectation over all actions or taking a max over all actions. So they are best illustrated with the backup diagram. So the big green nodes are the state nodes. The little blue nodes are the action nodes. So if your backup diagram has max over all actions, then it's a Bellman optimality equation. If it doesn't, then implicitly it's taking expectation. So it's a Bellman expectation equation. So you can always go from Q to V, but not vice versa. You can only go from V to Q if you have the MDP model available. In this chapter, it is assumed to be available, but in next chapter, we'll discuss model-free learning where it is not available. So policy evaluation tries to predict value function for given policy by solving Bellman expectation equation. So it can be solved for small systems with a MATLAB or some other symbolic math solvers. But in general, if the system is large, you use iteration. So any recursive equation can be turned into a iterative update equation. So you assume initial value and iteratively plug in the same value to the right-hand side and update the value until convergence. So the gray tool, I rewrote this slide to make it more clear. So the environment is deterministic, and the agent has a random policy. So Bellman expectation, the backup diagram, I added this branch factor, BF, is 4 because the agent has 4 possible actions: left, right, up, and down. Whereas the branching factor for the environment is 1 because the environment is deterministic. For the same state action, there's only one possible S prime. So for deterministic environment, you can rewrite the Bellman expectation equation to be a little bit simplified because there's only a single S prime. For SA, you don't need the other sum over S prime. So if you're trying to solve for V pi A, so taking the first expectation, you have A has 4 possible actions with the uniform random policy. It has the 0.25 probability of going in each of the 4 directions. So Q pi AL is the Q value function for agent in state A going left. And you have three additional Q functions.
Sorry, Songhua.
Yes?
It should be 0.25 times 0.7 on the first example, VA.
Oh, no, because going left and going up has the same Q.
Okay, so you have it in the end as well? Okay, oh, that's right. Going both.
Yeah.
Yeah, sorry.
So going up and going left, they both hit the wall, so it stays put.
Yeah, sure.
Yeah. But going right takes you into B and gives you 5 reward. And going going down takes you into C and gives you 0 reward. So once you get the Q, you can just take a average based on random policy and get the V. Similarly for V pi B and so on. And then if you plug in this set of equations into an equation solver, you get the solution. So B seems to be a good state because it has 3 actions. 2 of them lead back to B and give the reward of 5. That is up and right. So it seems to be more profitable to be in B, whereas C is a little bit further out. So it must go through A and D to get to B, the place with the reward of 5. So it has a lower reward of 2.2. And A and D are symmetric. So they must have the same value function. So did I say reward? So it's a value function. Value function is the cumulative expected reward. So based on your intuition, it fits your intuition. So, okay, any questions on this? So iterative policy evaluation example, I went over this last time. Did I? Yeah, I think I did. Yeah, I did went over it. So this picture shows that the value functions have not converged at k equals 3, but the policy has converged. So even if you go for many more iterations, the values keep changing, but the policies are stable. So if you are using the policy evaluation as part of the policy iteration, it's not necessary to wait for convergence of the value functions. As long as the policy is stable, you can move on to the next iteration. So policy iteration iterates between evaluation of policy V pi and improvement based on the greedy principle, that is taking an argmax of A over all actions. So to get a better policy based on the current value functions. So that's a policy iteration. I showed this example where you start with a uniform random policy. So it's similar to the previous one, except the previous one was too simple. So you reach the optimal policy in one step. So to make the this example more interesting, they added a few obstacles, the blue blocks, and not obstacles, traps. So if you go into it, you can go into it, but you get a -10 reward. So so with the initial random uniform random policy, you get very bad rewards in every state, except those to the upper left. So the MDP, did I say the yeah, the reward is -1 in all other states and -10 in the blue states. So you can think of it as a pessimistic view of life. Every day it brings you more pain. So you just try to end it all and go into the exit state on the upper left, where the episode ends. So the optimal policy it should be this, right? Avoiding the blue states. They're just more pain in life, and go into death quickly. So so initially you have a uniform random policy. So as indicated by the 4 arrows in every state, so you're wandering around in this great world with no purpose. So you don't know anything. You don't know the goal. You don't know there's obstacles or traps. You're just wandering around. So you run into the blue state very often, and you get a very minus negative rewards and with very minus, very bad value functions. But then after one policy improvement iteration, already the policies are looking much more reasonable. So you have a general trend of going in towards the exit, except for the bottom row. So the exit point is the only point where you have a positive feedback. So its effect will propagate through the grid with multiple iterations and gradually reach the lower, the bottom row. So as you go with many iterations of policy evaluation and policy improvement, so every time you perform evaluation, say starting from this policy here, -15, you evaluate the policy. So previously is pointing left, and now the new policy is pointing up. So you evaluate the new policy, you get -6 with a higher value. And then you based on the -6, this value brings the next grid's policy to the right to point to the higher value. So as a result of this improved value function for -6, you can cause your neighbor's policy to become better. Once this guy's policy is better, then it gets a higher value in the next policy evaluation step of -7. Then this guy has an effect of forcing the next grid policy to point to it instead of pointing upwards. So, and then this guy gets a higher value and affects the next grid to point to it from up to right. So as you can see, the effect is propagating from right to left on the bottom row. Eventually, every grid sees the light and has the policy of going right on the bottom row. Okay, is there any questions? So in this case, the value function has converged, but in general, it may not converge. Policy often are stable, often long before value function converges. Value function, I should say value functions, because every state has a value function. So here's another example where you're running thousands of iterations to reach convergence for the value functions, but the policy has stabilized long ago, so you're wasting time. So that's policy iteration. Value iteration does not have an explicit policy pi in the algorithm. Instead, it simply computes the value for every state and outputs a optimal policy at the very end by taking an argmax. So generalized policy iteration has policy iteration and value iteration as special cases. So I thought, okay, delete these figures. So so policy iteration, where are my figures? Oh, here. The policy iteration evaluates the value for a given policy until convergence, where convergence is defined as with the theta parameter to define accuracy of estimation. So smaller theta means that you must converge to a tighter constraint. So, but for generalized policy iteration, you don't have to iterate until convergence for policy evaluation. You can simply run it for number of steps that's maybe larger than one, but less than that needed for convergence of VS. So there's a theorem that says the generalized policy iteration will converge regardless of how many steps you run policy evaluation. So policy iteration and value iteration are two extreme cases of GPI. Policy iteration runs policy evaluation until convergence at every iteration. value iteration runs policy evaluation for a single step, and then improve policy implicitly by defining the new Q value function. The new value function, because here we have the MDP model, so knowing V is equivalent to knowing Q. There's no, you can easily convert between them. So here, you do one single iteration of max A, and then you loop for the next to keep on updating the V. So you can view this single line in the loop as a single step towards policy evaluation. So I think this single line includes both policy evaluation and policy improvement implicitly in the single line. So so VI is faster per sweep, because per sweep you're only doing one step, whereas PI is slower per sweep, but it requires fewer sweeps, where VI requires more sweeps. So here's a toy example, MDP with a single state S, a single action A, with reward 1 and gamma 0.9. So by definition, you can get the value function from computing the return, simply infinite sum of the rewards at every step. This is a geometric sum and turns into 1 over 1 minus gamma. You can do a policy iteration by first doing policy evaluation, plug in the equations, you get V equals 1 plus gamma V. You can solve for it to get 1 over 1 minus gamma. So a policy improvement policy is already stable because there is only one possible action. There are no other choices. Value iteration, you can plug in the max A. By definition, Q is equal to 1 plus gamma V. And there's only one A, so you have 1 plus gamma V. V star. Equal 10. So, and then you can solve for the V star, which is also equal to 10, and you take the argmax to get the optimal policy, which is also a single choice, A. So that's a very simple toy example for policy iteration and value iteration. I have this mini Great Wall example. So I took many examples from other places, but I made this one myself. So I'm very proud of it. So here's the transitions with two terminal states. A has value function minus 10, or D has value function plus 10. So you can think of a painful life. Every day is minus 1 reward, and then you may die and go to heaven, go to D, or go to hell with A as two terminal states. The dark squares denote obstacles which the agent cannot move into. Discount factor is 1 for simplicity. So environment is deterministic or stochastic. So when it's stochastic, then it may go into your movement direction with probability 0.8 or to the left or right, each with probability 0.1. If it's blocked by an obstacle in any direction, then it stays in the same state with probability of moving in the blocked direction. Moving in the blocked direction. So here's the policy evaluation of uniform random policy denoted by the triangles. So the random policy has the all the probabilities in 4 directions at 0.25, and you can do policy evaluation for deterministic environment. And so the backup diagram has branching factor 4 because it has 4 possible actions. Environment is deterministic, so branching factor is 1 for the environment. So you have 4 choices of Q pi, and in state C, you may go left and get -1 reward and go into B. You may go right, have -1 reward and plus D's value function. You may go up and get -10 as the value function of A. You go into A. Or you may go down and get reward -1 and the value function of E. So these two are unknown. These are by definition. But these two, V pi B and V pi E, are variables you need to solve for. And V pi B, if you go left, right, left, up and down, you all run into the wall. So you all stay in B. If you go right, you go into C. V pi C is still unknown, so it's a variable. In E, similarly, if you go left, right, and down, you stay in E. Otherwise, you go up, you can go into C. So this set of linear equations can be solved to get the value functions -6 for C, -10 for B, and -10 for E. So based on the value functions, you can perform policy improvement by taking the argmax. So when you are in C, and right now we're taking an argmax, that means that we're not actually taking any actions. We're looking at 4 directions and see which one is the best. So if we look left, we can see that, okay, I'll get a -1 reward plus B's value function, -10, so I get -11. If I go right, I get +10 as the next value function, so I get -1 plus 10, which is 9. If I go up, I get total of -11, and if I go down, I get -11. VE, yeah, -11. So argmax of these 4 Q value functions is this guy. So going right. So when you are in B, if you go left, up, or down, you all get a return back into B. because you hit the wall. So the total value function is -1 minus 10 is -11. But if you go right, you go into C. So we know C has -6 as the value function. So you have -7. So this right direction is the argmax. And similarly for E, the up direction is the argmax. So now after the policy improvement, we already have the optimal policy. But we cannot be sure until we run another iteration. So now we have a deterministic policy because in every state, you only have one choice, one best action. If you had two directions with the same value function, then you can have a stochastic policy. You can choose between them with equal probability. But if you don't have a tie, then the policy iteration will always return a deterministic policy. So based on the deterministic policy, we run policy evaluation again. Now the branching factor for the action is 1 because there's only one single possible action in every state. So our job is simplified. So for C, we can only go right. So the Q pi CR is -1 as the reward plus a 10 as the value function in D. So there's only one Q in this case. That's to the right. For B, it's only one Q, BR. And for E, there's only one Q, EU, up. So we can solve the set of linear equations to get the new value function, 988. And based on the new value function, again, you look around. While standing in C, you look left. Say, if I go left, I get -1 plus 8. If I go right, I get -1 plus 10. And so on. So you can see that argmax, the best action is to go right. Now, while in B, the best action is to go right. While in E, the best action is to go up. So now we have run 2 iterations of policy iteration, and the policy has stabilized. Sorry, here's another typo. Branching factor here is 1. So this policy is the same as the previous iteration's policy improvement, this policy. So the value functions happen to also converge, but it may not converge in general. But in this case, both the value functions and the policies have converged. So we can declare victory, and we have found the optimal policy. So that's for the deterministic environment. Let's look at the stochastic environment, where if you go in one direction, the environment may turn you into left or right directions. So now, the branching factor for the environment is 3 now, because there are 3 possible outcomes for the same state action, which means that for when you're C going left, you either go into B with 0.8 probability, or to A with 0.1 probability, or to E with 0.1 probability. And you know VA is -10, so you plug in VA to get this equation. If you go right, you have this equation, because VA and VD are all known. And similarly for up and down. So these terms, so these three terms correspond to the branching factor of 3 for the environment. Whereas these four terms correspond to the branching factor of 4 for the action, for the agent's action. So last time I put everything in a single formula and it was really messy. But now I put out the Q's and it makes it much easier to understand. So V pi B similarly, and V pi E. And once you get the set of linear equations, you can solve by analytic solution. Because the system is small, we can use the analytic solution. Otherwise, we need to use the iterative method to get -6, -10, -10. And you run a policy improvement. So this now we have a branching factor policy improvement, branching factor of sorry, I just copied the slide. So still policy improvement should be a branching factor is environment random policy for possible Qs. Did I make a mistake here? So policy evaluation gives you the V's, and then you run policy improvement. Okay, yeah, this is 3. Yeah, the branching factor for the environment is still 3. So the improvement step is similar to the last time. So we have gotten the optimal policy after this step. And now notice the policy branching factor has changed to 1 now for the action branching factor, because now we have a deterministic policy. So V pi C is equal to only 1 Q term, and V pi B and V pi E. Solution is 6.53, 5.3, 5.3, and policy improvement. So you can get the same policy. So now we have found the optimal policy because it's now stable. Why do I always have branching factor is 3 for the non-stochastic environment? Okay. So now let's try value iteration for the deterministic environment. Deterministic, so the branching factor for the environment is 1. Now to make the iteration converge faster, we can use in-place updates. That is, typically we have the Q. 1 is a function is assigned a value based on previous iteration values, but we can we can update, we can use the V1 in the current iteration directly for the computation of the value functions of B and E. So this way we can converge faster instead of using the V0 at this iteration. And next iteration, we see the new value of V1. We can use the V1 directly. So now we run value iteration. So the reason that we update V1C first is that it's closest to the sink nodes, to the terminal nodes. So all the rewards back propagate from C back to B and E. So if you update C first and use its V in the current iteration, we can accelerate the convergence process. So now the difference from the policy evaluation is the max. Instead of expectation, we take the max of the 4 Q values. So Q1, if you are in C, you go left, you go into B, you get a -1 because all the values are initialized to 0. Let me see the policy evaluation of deterministic policy. Okay, so if you go right, you go into D and get a total of 9, and go up, you get -11, and go down, you get -1. So taking the max over all the possible Qs, you get 9 as the value function for state C. And for B, you get +8, and for E, you get 8. So if you run another iteration, you actually get the same result. So if you plug in, yeah, I should really run it, but I think I skipped one step. But you can try one more step and show that it has converged. So now the last step in value iteration is to get the optimal policy by taking the argmax, which is the policy we expect. Okay, so value iteration for stochastic environment. Now the branching factors are 4 for actions and 3 for environment. We again use in-place updates. Now we have in the from Q for QCL in C you go left. You can have actually go into B or A or E with different probabilities. If you go right, you get D or A or E. So that's the branching factor of 3. And then you take the max over the 4 possible Q value functions. You get a plus 6 as the value function for V1C. And plus 3.8 for value function of V1B and V1E. So, and then you take the argmax to get the actual greedy policy. So, okay, so that's the example. Yeah. So what if you don't have the model? So I have been discussing planning based on the MDP model, but if you don't have it, you can use a model-based RL by first learn empirical MDP model, estimate the model P from state take action, what's the probability of next state and the reward. By executing some policy, maybe random, and keeping track of outcomes R and S prime for each SA in the observed episodes. And then once you have the empirical estimated MDP model, you can use the policy iteration or value iteration to get the optimal policy. So this step is called planning, because it's not learning, because your step 2 is just planning based on a known model. Step 1 is learning a model. So here's an example. You have 4 episodes, BCD, exit, BCD again, ECD, and ECA. So suppose you want to calculate the C's. From C, the probability of transition by taking an action. So from C, you can see that 3 of the episodes, C goes into D, taking the right action, going to D. Whereas in one episode, the right action brings it into A. And then you can simply say probability of getting a -1 reward and going to the next state as prime equal D is 0.75, and and going to A with probability of 0.25. So yeah, so that's the end of the MDP planning chapter. Any questions? So let's take a little break and come back at 4 o'clock. So I'm following the book pretty closely. So last lecture we covered chapters 3 and 4. Now we're discussing chapters 5, 6, 5 and 6. So now we're in the model-free world where we don't have the MDP. It's unknown, and we need to learn by exploring the environment. So MDP, here's one example MDP. A car transitions between cool, warm, and overheated. But now we have only the states. We don't have any knowledge about the transitions and the rewards. We must trial and error, learn the optimal policy. So IR, there's no supervisor, only a reward signal, maybe sparse. That's in contrast to a supervised learning or imitation learning, where you have immediate feedback in every step. Here we have maybe a feedback at the very end of the episode. And feedback is delayed, not instantaneous. And sequential non-IID data. Agent's actions affect the subsequent data it receives. So we discussed this IID in the imitation learning lecture. So in model-based IR, you learn an MDP model first, and then solve for the optimal policy with a policy iteration or value iteration. With model-free approach, the shaded area, you learn the optimal policy without learning MDP. So there's a value-based, policy-based, and actor critique, which is hybrid. But I'll discuss value-based approaches in this lecture. So here's an analogy of model-based and model-free. So suppose you want to compute the expected age of a group of M students. So if you know the model, that is, you know the probability percentage of students with a certain age, A, then you can do a weighted sum to compute the expected average age. So EA is sum A, PA times A, where PA is your model. But without model, you can collect samples of ages of the students. With n samples, where n may be much less than m, you can estimate the expected age. So with model-based IR, you first sample n students and ask for their ages and build an estimated model, p-hat. Then use p-hat to compute the expected age. So why does this work? Because eventually you'll learn the right model if you sample enough. For unknown PA, you can also do the model-free IR approach, where you randomly sample n students and ask for their ages and then compute their expected age directly without getting the model P. So this works because samples appear with the right frequencies. So this is not IR. This is really analogy, not the IR problem. And also the notation, I wanted to explain a little bit. So So a capital A denotes a random variable where a lowercase a denotes a of the specific value of the random variable.
Songhua,
Yeah,
what is the num a? Is it should be sum or is it a numerator or some?
number. So number of students with a certain age. Say number of students that's 20 years old. The number the num 20. I should really explain it a little more. So if you sample n students and you get 50 students with age 21, then the probability of age 21 is 50 minus or divided by n, right?
So this
So
num is 50 or what?
so num a is the number of students.
So it's a vector or something.
No, it's a single number. Oh, it's too.
Okay, so the A is age like 21 and a number of 21s.
Shouldn't capital A be the set of all possible ages? And then PA is P of small a, the probability of a certain age to appear, and A is the age.
Yeah, small a is the specific age, whereas a is the random variable of. If you view every student's age, represent the age with a single random variable, then the taking expectation is taking sum a and PA times a, right? So expectation over random variable.
Yes. Yeah. No. Yeah. I was just saying for this particular example of the age. No, or wasn't that the discussion about? Or?
So suppose you have a distribution of ages. Maybe age 20, you have 50%. Maybe age 21, you have 50%, right? So this distribution is a random variable a with two possible values. Small a could be 20 or 21. So the expectation of random variable big A is 20.5, right? So that's the
Yes.
capital letter denoting a random variable. Okay, so that's just a very small example to show what is model in model-based. So I'll first discuss Monte Carlo methods, then TD learning, then StarSalk and Q-learning. So Monte Carlo methods have prediction first and control. Prediction is just policy evaluation. So consider episodic tasks for MC-based prediction, where you have a finite length episodes and value of a given state for policy pi is to start from the state S and taking actions based on pi and counting the cumulative reward, denoted as GT, with the discount factor gamma. To estimate V pi S or Q pi SA, you can get all trajectories containing particular S or SA and compute the cumulative return for each trajectory starting from S or SA and average over all trajectories to get expectation. So at every state, so each circle is a state, you have a branching factor. The branching could be due to policy, could be due to environment. So, and then you a specific episode is a path from start to end of the episode through this a tree of possible next states. And as you can imagine, if the branching factor is very large, these possibilities, possible paths, the number grows exponentially. So you may need many samples to get accurate estimate due to random policy and stochastic environment. So I think the early chess playing game that beat Deep Blue, that was based on Monte Carlo method, where they simply well, it's exhaustive search, not really Monte Carlo. So they are more brute force. Here we're, if you're sampling many trajectories starting from a state and averaging to get the value function, this is Monte Carlo. But if you're exactly trying all the possibilities with no sampling, that's exhaustive search. So here's MC prediction. There are two variants. One is first visit, where state S may be visited multiple times in the same episode. So if it's first visit MC, then you estimate V pi S as the average of these returns following first visits to S. If it's every visit at MC, then you average the returns following all visits to S. So the figure shows the every visit MC. So initialize the VS arbitrarily and typically all zeros, and loop forever, generate an episode following the policy, and you go backwards from the last non-terminal state st minus 1. St is the terminal state. So starting from st minus 1, you accumulate the rewards, adding a discount factor, and do an average over the past returns from state ST. So the average could be done with a running average. So here's an example. This is an episode where you start from the left and going until to the right until you hit the terminal state. So you work backwards. The 1, 2, 3, 4, 5. Yeah, this guy is 5. G5 at this point, its reward is. Did I miss something? I think I forgot to. Oh, okay. The edges are labeled with the rewards on every transition. So okay. The last one is 5. G5 is 0. The next one is G4. It's reward 2 plus. That's the only reward of 2. And G3 is 1 plus gamma times R5, which is G4. That's 1 plus 1. And G2 is R3. That's 7 plus gamma times R4. That's 0.5 times 1 plus 0.25 times 2. You can do the computation this way, or you can plug in G3 for this latter term as G3. So by working backwards, you can do less computation. If you go forward, it's fine. If you go forward, you just simply recompute everything at every step. But if you go backwards, you can reuse some of the computation. So that's why in the pseudocode, you go backwards. So one problem is exploration. So we have learned epsilon greedy before, or epsilon soft. So for stochastic policy, where you take the current optimal policy with probability 1 minus epsilon, and epsilon is for exploration. But if you have a deterministic policy, you cannot have epsilon greedy. So the way to do exploration is exploring starts. So for example, in this grid world, you have the deterministic policy, but it may not be optimal. You want to improve it by doing Monte Carlo. You want to evaluate the Q value at every position. So you can specify that the episodes start in S0, A0, the blue state, and every possible SA has a non-zero probability of being selected as the start. And from S1, A1, follow policy pi for action selection. So the first is the blue S0, A0, because you wanted to compute its Q value. So you take the first step, the blue step. Then afterwards, you follow the current policy, the red arrows. So by placing the initial starting point of every episode randomly on the grid, you can do exploration. even with a deterministic policy. So this is the actual execution of this episode. So that's for MC for prediction. For MC for control, this is the previous slide on policy iteration, where you have policy evaluation followed by policy improvement. Now with MC exploring start, you can do generalized policy iteration. So after every episode, the observed returns are used for policy evaluation. And then the policy is improved at all the states visited in the episode. So generate episode following policy pi, a loop for every step of episode. Going backwards, you update the returns and perform average to get the Q, and immediately you take argmax of the Q. That's every step of the episode. So that's not evaluating Q to convergence. That's more like this. So you are doing very fast. One step compute update of Q, and one step argmax A over the new Q. So it lies between two extremes. The policy iteration we learned before, the policy evaluation must achieve convergence up to some level of approximation, the theta parameter. For value iteration, only one iteration of IPE is performed between each step of policy improvement. But here, we are performing the policy evaluation in an episode by episode basis. So here's one example. So you have an agent initially in this one-dimensional grid, the uniform random policy of going left or right. So in one episode, it wanders around until it hits the goal and gets a reward. Then the QSA for all the states visited in the episode are updated, and the policy is improved based on the argmax QSA. So the figure shows that only one state's policy, this guy, is improved, but in general, it's possible that multiple states' policies are changed. So after sufficient exploration, all states' policies may converge to the optimal pi star, that is pointing right towards the goal, the cheese. So if some states are not explored enough, for example, if the leftmost state is never visited, or it's visited only a few times, and the updates to the Q is not enough to overcome a bad initialization, then its policy may not be optimal. So sufficient exploration is important for converging to the optimal policy. So epsilon greedy, we saw it before. So it selects a random action W with probability epsilon. Select the greedy action, which is the argmax. Greedy action. Argmax with probability 1 minus epsilon. So with a total possible actions in state S, select each non-greedy action with probability epsilon divided by the size of the set, the greedy action with 1 minus epsilon plus epsilon divided by that. So the because the random action includes the greedy action as one of it. So for epsilon greedy, you have equal probability for all non-greedy actions. But for epsilon soft, it only has a requirement that every policy A is selected with a lower bound probability, but it may have some other distribution instead of the equal distribution for epsilon greedy for non-optimal actions. So it's a more general form of policy specification. Epsilon greedy is a special case. So you may think of a softmax with additional lower bound, for example, could be a soft policy, but just the soft max doesn't give you a lower bound on the probability. So the optimal epsilon soft policy or epsilon greedy policy is the highest best policy with the highest value in each state among all epsilon soft policies. So in general, it performs worse than the optimal greedy policy pi star. So in general, the greedy policy with the optimal value Q value function is the optimal policy. So if you add epsilon soft to it by having some exploration, the resulting policy is worse than the greedy policy, deterministic policy. Worse than the optimal greedy policy. This is deterministic. So by optimal epsilon soft, we mean that it is optimal among all epsilon soft policies. But if you expand your view towards all possible policies, then it's generally worse than the optimal deterministic policy. So here's the generalized policy iteration. We saw GPI with Monte Carlo for exploring starts. Now we see we're not using exploring starts. We're using epsilon soft policy. So first, the policy is not deterministic. It's epsilon soft. And then there's no exploring starts. You can start from fixed S0. So in the previous, we must choose S0 randomly, such that all pairs have probability higher than 0. So that's exploring starts. But here, we don't have to do that. And the third difference is the epsilon soft policy with the small probability of choosing the non-greedy action. So that's on policy MC control. Now we move to off policy MC prediction. So off policy MC control is omitted due to time constraints. So what's off policy? It means that you improve and evaluate a different target policy pi from the behavior policy B that's used to select actions. So the behavior policy may be more random and more adventurous than target policy to facilitate exploration. Could be a uniform random policy. So the behavior policy must cover the target policy. So if action is possible in target policy, it must also be possible in behavior policy. Otherwise, agent will never experience the SA pair. So for on policy, you improve and evaluate the behavior policy B that is being used to select actions. So the behavior policy is the same as the target policy. So importance sampling. So we want to estimate a expected value of a random variable x with distribution pi by sampling from another distribution rho. So the capital X is the random variable, small x is the sampled value for x. So by definition, expectation of a random variable based on distribution pi is sum of small x, the a particular value, times its probability pi x for all possible x. So we assume the x is a discrete number. Otherwise, we need to use integrals. So and then you can do a switch of define rho is pi xi over bxi for each xi, and then the sum is equal to b times rho times x. And then you can convert it into expectation over the distribution of b and rho times x, which is can be evaluated by sampling, drawing samples from the distribution B, behavior policy. So here we're discussing general random variables, not really reinforcement learning. So we compute expectation of random variable x with distribution pi by sampling from another distribution B, and then performing weighted average with weight rho x, where rho is pi over b for each xi. So let's look at one example. Say we have two possible distributions of a random variable x. With bx, you have with 85 probability, you have a value 1, 5 probability you have value 2, and so on. And pi x is another distribution among the 4 values. So you wanted to compute expectation of x with distribution pi. So we can simply compute it 0.3 times 1 and 0.4 times 2, and so on. So the expected value is 2.2. That's our ground truth. But we sample from B instead to evaluate the E pi x. So we draw the first sample from B. Suppose we get x is 1 with the probability 0.85. So the EBX, based on the formula, is only a single item, and rho is the pi xi over bxi, which is 0.3 divided by 0.85. That's rho. Yeah. So second sample, you get 3 with probability of 0.05. Then you add one more term of 3 times 0.1 divided by 0.05. And third draw, you get a 1 again. So you add another term here. So after 3 samples, you get a estimated expectation value of 2.24, which is pretty close to the ground truth of 2.2. So that's the idea of importance sampling. We'll see this idea again in policy gradients. So the basic concept is that you have the distribution B available, and you're evaluating the expected value of X under another distribution pi. So you cannot simply do a average over your samples. You must do a weighted average. So coming back to reinforcement learning, we define a trajectory over behavior policy B as the sequence of starting from ST and the sequence of actions, the probability of the sequence of action state. And by using the Markov property, you can rewrite this term as a separate B term and P term, denoting the behavior of action selection and the environment state transition to the next state. And the rho term we saw before is probability of trajectory over under pi, the target policy, over the trajectory under B, the behavior policy, which is only difference is the pi here and B here. And these two terms cancel out. So we have this term. And for we can work backwards to compute more efficiently. So having the weighting factors, we can do off-policy prediction. So remember the previous, we saw the MC prediction with Monte Carlo sampling. We simply generate episodes and average the returns for a particular state to get its value function, expected value function. But now we are doing the off-policy MC prediction, which means that we are trying to evaluate a policy pi, but our behavior has a policy B, different policy. Whereas in the previous on-policy approach, you have the same policy to be evaluated and policy to be executed. But now we have a different behavior policy. As a result of this difference, we must add this weighting factor, W. By multiplying W to G before adding it, updating the G used for calculating the value function. And the W is computed based on backwards from episode, from the terminal state of the episode backwards, and multiplying a factor of for in a given state as k, you for the target policy, what's the probability of an action actually taken in the episode, divided by the probability of the action taken in the actual behavior policy. So that's the how you get W, and then then you multiply W to get a weighted average instead of the original just average to compute the value function. So it's called off policy because you're improving and evaluating a different target policy pi from the behavior policy B that's used to select actions. Therefore, you need to add the actual weighting. The reason you want to do that is because the behavior policy may be much more random, more adventurous, which allows more exploration, whereas you can the target policy may become more and more deterministic as you are training your policy. Okay, any questions on Monte Carlo methods? Okay, so let's move on to TD learning. So let's first introduce the concept of exponential moving average. So running average update is say you have a stream of incoming measurements of a variable x, and you need to update the average not by recomputing the average every time, but by keeping a running average. So you can define a weighting factor alpha, and every time you have a new measurement coming in, you weight it by alpha, and the old value weighted by 1 minus alpha. Or you can rewrite it as this form. So a shorthand notation is simply update the running average with a new value based on weight alpha. So if you write out this running sum, it's alpha times the most recent measurement xn plus 1 minus alpha, its previous average value, which can be written as recursively as alpha x n minus 1, the next recent measurement value plus 1 minus alpha, and so on. So if you take out the it's xn plus 1 minus alpha of minus alpha squared. Am I missing something here? Xn is alpha xn. Oh, okay. I got it right. So this should be alpha. And then is 1 over alpha is this guy. 1 over alpha is this guy. Yeah, so that's right. So so if you rewrite this moving average in this form, it clearly shows that it weights the more recent samples more. So the most recent sample has weight of 1. The next recent has weight of 1 minus alpha. The previous one has weight 1 minus alpha squared. So it gradually forgets about the past. So distant past values are wrong anyway for value function estimation. So it's not a simple average. So it's an uneven average. More recent values are weighted more than older values. So decreasing the learning rate alpha gradually can give a converging average. So TD learning, if you recall the Bellman expectation equation we saw before, if we solve it with dynamic programming, we need the P, the MDP model P. For TD learning, we're model free. We don't have the MDP model. So we evaluate the expectation by sampling. So expectation, here the two sums is replaced by a sampling. That is, capital R is the random variable. We're sampling from the random variable, plus gamma, capital V is the a random variable of the next state value function. And that's our target. And we are updating our running average running estimate of V with the new target value with a learning rate alpha. So the term target minus current value is the TD error. So ideally it should reduce to 0. So tabular TD, right now we are in a tabular world. We're not discussing neural networks yet. So comparing it to Monte Carlo, we saw before, Monte Carlo updates the value at the end of each episode, working backwards from the end of the episode, from the terminal state up to the starting state. TD updates a value at every time step. So this is called bootstrapping, S from S prime. So you're estimating VS prime and then using the estimated value of VS prime to update the VS. So let's look at one example of a random walk. So this is a one-dimensional grid. Agent has uniform random policy W with equal probability of going left or right at every time step. Environment is deterministic. All episodes start in state C, the central state. Episodes terminate either on the left or on the right. Reward is 0 on all transitions except 1 for terminating on the right. So that's a good state. Discount factor gamma is 1, learning rate alpha is 0.5. So the value of each the state is the probability of terminating on the right when starting from state S. Based on the definition, based on the only reward you get of 1 of exiting on the right. So we can write the Bellman expectation equations. So set of Bellman expectation equations. So VA is on the left it's a 0 and it ends. On the right is VB. So 0 point it's 0.5 times VB, and transition itself has a reward of 0. VB has 2 possible choices, left or right. So it's 0.5 VA plus 0.5 VC, and so on. So VE has a 0.5 going into VD with reward 1 and 0.5 of going into the terminal state with a reward of 1. So I should make it more clear. Should be 0.5 C dot 1. So we can solve this set of linear equations to get the value functions shown on the figure. So suppose you run one episode from C to D to E to terminal to exit. Now based on TD, VC, you update the VC with the TD target, which is 0 plus gamma times the VD. All V's are initialized to be 0.5. So this guy has 0.5 as a result. That's after that's when you are in state C. When you are in D, you look ahead one step to see next state is E. So that's the RT plus 1 plus gamma times VE. And then you get 0.5. Next state VE, your next state is T, based on the trajectory, based on the episode. So now you have a reward of 1 by going into the terminal state. And VT itself is 0 minus 0.5, so you get 0.75. So that's the result of TD learning after this CDET trace. So for the Monte Carlo, at the end of the episode, you get a reward of 1, and that's your only reward. So that's also your returns. And then you update the values of CDE, that's all the states visited in the episode. So initially, initial value 0.5 plus alpha times 1, the return for the entire episode, minus the old value 0.5, 0.75. So CDE all have the updated value of 0.75. Now let's look at another episode based on starting from the end of the previous episode. Now we go from so every time you exit on the right, you return from to C and restart. So from C you go to D and E. Now at the state C, your TD update gets you 0.5 again. For D, your TD update gets you now the VE has changed before, right? VE last time we updated it to be 0.75. So now it's 0.75. And now the D's value is now 0.625. But for MC, the episode has not ended. MC learns at the end of episode. So for MC, there's no update. So the values stay at 0.75 as before. Now the next sequence of part 2 of episode 2, you continue and you go E, D, C, you go left. Now for TD, a value of E is now the reward plus gamma times VD, because your next state is D now. You're going left. So plugging in the value for D, which is 0.625, you got a new value for E, 0.688. And from D, you go left, so your next state is C. The TD update gives you 0.563. But for Monte Carlo, again, no update, because the episode is not ended. And then keep going, again, you go CDE. So from C, you update based on the next state of D. And from D, you update based on next state of E. So the TD update's next state is dependent on your direction of travel. And again, for MC, there's no update. So this example shows you that TD can perform more frequent updates than Monte Carlo, and it often converges faster. So here's an example of a random walk evaluated for MC. The red lines with a different alpha learning rates, and TD with different alpha. So TD generally converges faster than MC, but with higher learning rate, say alpha equals 0.15, error reduces faster but results in higher final error. So TD may converge the wrong value. That's the bias in machine learning. So larger alpha helps achieve faster convergence, but introduce higher bias. So here's the MC prediction for the mini grid world. We saw before. You have 4 episodes. Last time we used the 4 episodes for estimating a model, transition model. Now we're using it for estimating the value function, model free, in the model free method. So in state A, you have a single state A. Where's it? A? That's the only one. So you exit with -10, so your value is -10. State D, you exit with +10, your value is 3 times. So you have times 3 divided by 3. For state B, you have you see it twice. So the first time the episode has reward of 8, -1, -1, 10. Second time is also 8. So the average is 8. State C, now Now in the first 3 episodes, starting from C, C is not the starting state, but it's encountered in the middle of the episode, but that's okay too. So 3 of the episodes, it goes into D. 1 of the episodes, it goes into A. So its value is the average among the 4 episodes. And state E, it has once it goes north into C, but so once from E to C to D, another time is E to C to A. So its returns are 8 and minus 12. So the average is minus 2. So for policy evaluation, if we knew the MDP model, we can derive VB is equal to VE. But the MC predicted value functions are inaccurate due to limited sampling, because we're estimating V hat B is 8, whereas V hat E is minus 2, whereas they are symmetric. They shouldn't be different. The reason is that you're just unlucky for E, because for B, both episodes 1 and 2 start from B and end in D with a high value, whereas for E, you happen to see 2 episodes starting from E and ending in either D or A. So that's why the predicted values are not accurate. If we sample more data, then we can estimate more accurate values. So in general, MC learning, MC prediction is not sample efficient, since the value function of every state must be learned separately. It's not aware of the sequencing of the state. Yeah. So if we look at TD learning, say with the deterministic policy, we saw, say we have 4 episodes of BCD. Then based on the TD update, we can first update, we get transition from B to C, we get reward of -1, and the VC is 0. So and C to D, you get a reward -1 and a value of 10. So episode 2, the same BCD, you get you plug in the old value of -0.5, and you get updated values 1.5, 6.75, and so on. So as you're running, you will keep updating the running average as your value function. So if you use in-place updates, in-place, no, I think this is not right. I shouldn't write this. Oh, okay. Yeah, let me delete this. The reason is that in-place updates is only for offline evaluation, where you can go backwards in a episode. But TD is an online method, so you cannot go backwards. You must, while you're in state B, you must update state B. You cannot wait until later. So yeah, I got confused here. This shouldn't be here. Yeah, so just to see, this is still in place update. So if you have a higher learning rate, you converge faster. Yeah. So here's the backup diagrams for Monte Carlo. You are running all the way till the leaf, till the end of the episode, the terminal state, and then you do a backup along the path for all the states encountered in the episode. For TD learning, you are doing one-step backup with bootstrapping, backing up, updating the VST based on VST plus 1. For dynamic programming, you're doing a full backup. So looking up, you can see that so TD learning has shallow backup and sample backup. It's based on sampling. Whereas Monte Carlo is sampling and deep backup. You run until the end of the episode. Dynamic programming is a full backup, but it's also shallow. It's a one-step backup. Whereas exhaustive tree search, that's a full backup and deep backup. That's typically not feasible for complex systems. Okay, so yeah, I think we are out of time. Any questions? All right, let me, so the exam time was set to be June 1st. So I'm thinking the exam is open book, so I think it will mainly consist of multiple choice questions and to make it easier to grade. So it shouldn't be too hard. I'll mainly take stuff out of the slides and ask you, say, I don't know, if TD learning is off policy or on policy, stuff like that. So the last class, I think I'll do a Q&A session. We can, you know, you can point to any point on the slides and ask me questions. So any issues on the lab assignment? Any difficulties?
Sorry, Xinghua. For the exam, is it possible just to make like a fake exam for training or something like that?
Sure. Yeah, I can make a mini fake exam to yeah, I think I'll do that in the last week when I know that how much I have covered. I think at least you know 4 or 5 days before the exam should be okay. A week before the exam date.
Yeah, that would be really helpful, at least because this subject is quite new and we don't have previous exams to get a sense of the questions and what do they cover for real. I know that you have quizzes here and there, but for the exam, it would be really great for a fake one or mini one for training.
Sure. Okay.
Okay. Thank you very much indeed.
Yes.
I will have a look, see if you can do it online directly in Canvas, maybe.
Yeah, sure.
And I can also mention I have some problems with this code racing stuff. I have now installed a new computer with Linux, the 20.04 version. So I'm installing now and will hopefully will have the lab tomorrow or maybe Wednesday.
Yeah, so I think we can have the, we're thinking of one additional lab, lab 5, but I think the deadline could be set to be after the final exam to give you more time and
Also time to read.
I think we can make it kind of extra credit because students are busy at the end of the semester. So yeah.
Absolutely, very
Yeah.
good idea. Mm. So it's not obligatory then. So if they want some extra, they can do it.
Okay.
On Thursday, the 21st, it's a red day in the calendar, so people don't usually work then. I don't mind being here at Thursday, but others don't work that day.
I see. Yeah, we 21st. I think let's cancel the day's class because I think we already have enough material. So we will just have the next class on 25th.
Okay.
Okay.
Very good. Yep.
Yeah. But I think the deadline for the project submission is still the 21st, is it?
The 20th for lab 4.
Yeah.
Zunghua, I'm sorry. The last assignment I had to handle it for many reasons later than my colleagues. So practically, I'm working with a shorter time with this one, as I mentioned before, because I don't have enough experience with machine learning, AI, and some of the Python aspects. So it should be due in 2 days, and I'm not sure if I can cover that up in 2 days.
I showed the lab 4 during the last lesson, so it might take half an hour or maybe 1 hour to make it. So it's no programming involved or nothing, just
okay,
understanding and reading.
Okay, understanding and reading. Thank you very much, Mr. Kali.
Yep.
Thank you.
Okay, so May 20th, yeah, so just a reminder. Let me see if anyone has submitted.
Yeah, two have.
Yeah, okay.
You maybe shouldn't show the rest.
Okay, good.
Yeah. Maybe it's a quick way to show the other one's answers. Good idea. So, and hopefully before that deadline, we will have lab 4, and then I will record a video for lab 5, and I will record a video for lab 5, so you can start working with that if it's a rainy holiday or something, or you want to be prepared in some way. So it's basically based on pixel graphics, which you should learn how to drive a car from that. And I think it's very interesting method, I hope, if it works. So it works currently in Colab, but it has to store some pictures and diagrams and so on, and that part doesn't seem to work very well. So I hope I will solve it tomorrow.
Okay, so see you next Monday.
Yep. Have a nice holiday.
Thank you.
Goodbye.
Thank you. Bye. See you.
Bye-bye.